Hello, welcome back. In this video, we'll discuss the Heisenberg Uncertainty Principle. The wave nature of atomic particles leads to some important inevitable consequences. The Heisenberg Uncertainty Principle is a result of those consequences. The uncertainty principle was proposed by Werner Heisenberg in 1927. Suppose you have an object with mass m moving along x direction with a linear velocity vx, then say m is the mass of the object, say vx is the linear velocity along x direction, and if you have a object like this that is having vx, which is the linear velocity, and this is the x direction, this is the origin. If the object is moving with a linear velocity vx, then one can easily find out its position and momentum. If you write the momentum of the object as px, because we have only the velocity along the x direction, or we have only the x component of the velocity, then you can write it as mvx. Similarly, one can also find its position at any given instance of time t prime. X at t is equal to t prime will be equal to vx t prime. So for a classical object that is in motion with certain linear velocity vx having mass m can have a momentum along the x direction which is given by mvx, and its position can be obtained using vx times t prime. But when you try to find out the position and momentum of a microparticle, it is not as simple as this. Reason being, every de Broglie wave can represent a microparticle. What are these microparticles? A microparticle essentially is a molecule, atom, electron, proton, etc. They are called as microparticles. In the case of microparticles, every microparticle will behave like a matter wave. So a de Broglie wave exists for every microparticle. Because a de Broglie wave is associated with a microparticle, we do not know the exact location of the particle in the wave packet, because the de Broglie waves are nothing but the matter waves, or they are the wave packets. And since we have the wave packet, the particle can be anywhere within the wave packet over its spread. As a consequence, it is impossible for us to find out the exact location of the particle in the wave packet. Further, in quantum mechanics, Schrödinger postulated that a moving microparticle is equivalent to a wave packet. Schrödinger postulated that a moving microparticle is equivalent to a wave packet. From the Schrödinger's postulate, we know that a moving microparticle is equivalent to a wave packet. In order to understand this postulate, we shall try to understand what is a wave packet. Suppose you have several waves like this. Say this one y1, this as y2, y3, y4 and y5. If you take the superposition of these waves, that is y is equal to y1 plus y2 plus y3 plus y4 plus y5. In fact, this particular wave represents a portion of the wave that is generated using the superposition of these 5 waves. Y is the superposition of y1 up to y5. Superposition means we add up the waves to find out the resultant wave, which is nothing but the superposition of the waves. These waves are having different frequencies, amplitudes, initial phase angle and wavelength. We are considering a set of waves which are having different frequencies, amplitudes, initial phase angles and the wavelengths. And we have taken in this example 5 such waves, taking the superposition of the 5 waves to obtain the resultant. The resultant looks like this, and this is what we call as a wave packet. When you take the superposition of several plane waves, you get a wave packet. The wave packet will have certain spread. This wave packet is spreading over delta x. We know from the Schrödinger's postulate that the moving particle is equivalent to a wave packet, which means the particle can be anywhere within the wave packet. It can be here, here or there. It can be anywhere within the wave packet. Since it can be anywhere within the wave packet, we use the probability methods to find out the probability of finding the particle at any location within the wave packet. By looking at the wave packet, one can say that the probability of finding the particle at the center of the wave packet is maximum and nearly zero at the ends. At the middle of the wave packet, the probability of finding the particle is maximum. and at the two extremes of the wave packet, we find the probability of finding the particle is almost equal to 0, which means the particle can be anywhere within the range delta x. At any given instance of time, you can have the particle within that range, that is delta x. The linear spread of the wave packet is delta x. The particle would be located somewhere within the region delta x. Therefore, there is an uncertainty delta x in the position of the particle. The uncertainty in the position of the particle is delta x. Since there is uncertainty in the position of the particle which is equal to delta x, the momentum of the particle at that instant cannot be determined precisely. Therefore, the momentum of the particle at that instant cannot be determined precisely. Since the uncertainty in the position is there, the momentum of the particle at that instant cannot be determined precisely, which means the location of the particle and the momentum of the particle cannot be simultaneously determined with certainty. In 1927, Heisenberg showed that the product of the uncertainties in position and momentum always will be of the order of Planck's constant. Delta x, delta px is greater than or equal to h bar by 2, where h bar is equal to h by 2 pi, where h is the Planck's constant. This relation is called as Heisenberg relation in one dimension along the x direction for the position and momentum of the particles. Now we can write this statement for the uncertainty principle in one dimension case as it is not possible to know simultaneously and with exactness both the position and the momentum of a microparticle. One can write a general statement for Heisenberg uncertainty principle in this form. It is impossible to measure simultaneously a pair of conjugate quantities with the same degree of accuracy. Here we are using a term called conjugate quantities. What are these conjugate quantities? Conjugate quantities are those quantities in quantum mechanics whose product will be dimensionally equal to the Planck's constant. For instance, the position of the particle and the momentum of the particle and energy of the particle and the time at which energy is measured. From this, one can write the other uncertainty relations that are applicable to the quantum mechanics. So we write delta x, delta px greater than or equal to h bar by 2. Similarly, we can write delta y, delta py greater than or equal to h bar by 2. Delta z, delta pz greater than or equal to h bar by 2, and similarly delta e, delta t greater than or equal to h bar by 2, delta mx times delta phi x is greater than or equal to h bar by 2. Delta x, delta px we have already seen. On similar lines, one can also write delta y, delta py is greater than or equal to h bar by 2, and delta z, delta pz greater than or equal to h bar by 2. Since we know that the dimensions of the Planck's constant is Joule second, one can also write delta E, delta T that is greater than or equal to h bar by 2. Because both energy and time are also conjugate quantities, we can write an uncertainty relation like this. Similarly, delta mx, that is the x component of the angular momentum, delta E is uncertainty in energy, and delta t is the uncertainty in time, means in the measurement of time, and delta mx is the uncertainty in the x component of the angular momentum, and delta phi x is the uncertainty in the x component of angle. Now we shall understand how delta x, delta px is greater than or equal to h bar by 2. Let us revisit the plane waves and the wave packet. If there are more number of plane waves used to construct the wave packet, then delta x will be small, otherwise it is large. Means if the number of plane waves used to construct the wave packet is more, then delta x will be small. On the contrary, if you have small number of waves that are used to build the wave packet, then we have the delta x that is large. And corresponding to each of these plane waves, we have a wave vector that is called as k. K is the wave vector. Wave vector is defined as 2 pi by lambda, And we know that momentum of a particle p is equal to h bar k. So one can calculate the momentum with the help of wave vector. Since we have several waves, one can calculate the maximum and the minimum of the momentum of each of these waves. The difference would be the uncertainty in the measurement of the momentum. Therefore, if you use a large number of waves, then the spread in the momentum will be large because we have a range of momentum values for the waves. As a consequence, uncertainty in the measurement of the momentum is large, and since delta x is small, we get the product that is greater than or equal to h bar by 2. The uncertainty principle holds only for the microparticles. It cannot be applied to macroscopic particles. Let us look at some of the applications of uncertainty principle. Using the uncertainty principle, one can prove that electrons cannot exist within the nucleus. The second one is one can study the behavior of the particle in a box. Thirdly, one can estimate the Bohr's orbit and the energy. This video we have started by saying that Werner Heisenberg has proposed the uncertainty principle in 1927. We have seen an example to illustrate how one can find out the exact position and momentum of an object of mass m moving with velocity vx along the x direction. We have seen the Schrodinger's postulate, which states that a moving microparticle is equivalent to a wave packet. We know that de Broglie waves are the matter waves. They are the wave packets, and we have seen how a wave packet can be constructed. Heisenberg showed that the product of the uncertainties in position and the momentum always will be of the order of the Planck's constant, which is delta x dot delta px greater than or equal to h bar by 2, where h bar is h upon 2 pi and h is the Planck's constant. We have seen the general statement of the uncertainty principle. We have said that it is impossible to measure simultaneously a pair of conjugate quantities with the same degree of accuracy. We have seen various uncertainty relations: delta x delta px greater than or equal to h bar by 2, delta y delta py greater than or equal to h bar by 2, delta z delta pz greater than or equal to h bar by 2, delta e delta t greater than or equal to h bar by 2, delta mx delta phi x greater than or equal to h bar by 2. We have seen how the uncertainty in position and momentum can be explained with the help of a set of plane waves and a wave packet. We have also seen the applications of uncertainty principle. We have said that uncertainty principle can establish that electrons cannot exist in the nucleus. We have seen that some of the concepts of the particle in a box can be explained using the uncertainty principle, and we also seen that the Bohr's orbit and the energy can be obtained using the uncertainty principle. Thank you.